All right, the moment we've all been waiting for. So we got our nice study music on in the background. We've got our awesome chart that we've been working really hard to derive out over the last 2 weeks with the lab that we did and all the breakdowns and the watching of the experiments that I did. And this was really the goal. So I've got copies of this on Schoology. I've got a filled out copy. I've got a blank copy if you want to print those out and have those with you. But if you don't have access to a printer right now, you're going to want to pause and record this down right now. So write this whole chart down because we're going to be referring back and forth to it. And you're really going to need it when you start to do your own. So I will pause for a minute and let you do that. Okay, that's going to be way too long, so you can just pause the video here because we'll just keep moving on now. So these are the main behavioral patterns that we kind of derived out from our experiments. We saw that when we wire things in series, the way the voltage across each of them worked out was that it was conserved, right? So the total voltage we applied to a branch, right, because everything in series means it's in the same branch or the same path of current. That's what we got up here. So it was conserved, right? So if we apply 12 volts to something, then the resistors wired to that branch will share those 12 volts. So the way we can kind of write that in equation form is, V supplied equals the sum of the voltages. Or in this case, V supplied equals V1 plus V2 plus V3 plus, however many resistors you have. Now we saw that when the resistors are nice and identical, well then that's wonderful. Then they just split it up equally and it's very, very easy to work with. However, when they're not of equal resistance, we see that things with more resistance use more of the voltage supplied to that branch, which should just kind of make sense, right? We talked about that as just the definition of being in series, right? Being in the same path of current, same current. And so when the definition of resistance is how many volts you need to get that same current, right? How many volts per amp, things with more resistance are going to absorb more of that voltage. And then we also saw that current through each element was the same. So regardless, they're just automatically equal. Again, kind of going from the definition of that, right? Series, same path of current. Series, same current. So the current through resistor 1 was the same through current resistor 2, through resistor 3, even back right through the battery. And it did not depend on resistance. Things with more resistance still had the same current flowing through them. Because again, series means same current. Now, when we went to parallel, things kind of reversed. They flip-flopped. We saw that, when we wire things in parallel, what we're really doing is we're forming whole new branches of the circuit. It's almost like hooking each one up to their own separate voltage source. So they behave independently from each other. And each branch gets the same full voltage supplied. So if you've got a 12-volt battery, every branch that you hook onto that is going to get 12 volts. And that does not depend on resistance. Doesn't matter if you have a big resistor, little resistor, anything you hook up to that voltage source is going to get that same 12 volts of voltage. And that might seem like a violation of conservation of energy, right? How this thing can only supply 12 volts. How can it supply, if you hook up 3 branches, that's supplying 36 volts. How is that possible? Well, because the idea here is that current is conserved through the parallel branches. So for each branch you hook up, the battery or the voltage source has to work harder and has to push out way more current for each of those branches. So what we find is that the total current supplied is being conserved, and that will add up through the branches. And this is not necessarily equal. It's kind of like we said here, but it's kind of the reverse, right? Branches with more resistance will result in less current. Because again, you got to think of them as just being in their own separate circuits. And when you have 2 resistors hooked up to, equal amounts of voltage, the one with more resistance is going to have less current flowing through it. Again, kind of by definition, right? Resistance is how much it will resist the flow of current. So resistance does impact the current in each parallel branch, but it's the kind of the opposite there, right? Here we had more resistance means more voltage. Here, more resistance means less current. And this is what we're going to be referring back and forth to as we go through this, right? And so the equations are kind of flip-flop, right? Here in series, current equals current equals current. Here, voltage equals voltage equals voltage. And then here, they're kind of like sum of equations, right? V supplied equals the sum of the voltages. And here, I supplied equals the sum of the currents.